All right, so we're going to continue in Chapter 6 talking about solutions, and with that we're also going to talk about collegiate of properties, which is concentration-dependent solutions that are dependent on not the identity of the particle that's being dissolved, but how much there is. Okay? So these properties, these physical properties will change based on how much of the solute there is in solution. Okay, and we call these the collegiate of properties. So collegiate of properties that change based on these concentrations of the solutes is vapor pressure, boiling point, freezing point, and osmotic pressure. Okay. So with vapor pressure, you don't actually have to calculate it. There is a calculation. There is a way to calculate it, but you guys don't have to do that. Okay. Vapor pressure of a solution results from the escape of the solvent, right? So we've talked about these vapor pressures that are established above, like water. When you let it evaporate, it establishes that vapor pressure above it. Okay. You could actually measure that vapor pressure. Now, you can change the vapor pressure of a solvent by adding something to it. Okay? If I add something to it, then that's going to allow it to change. Okay? So Raoult's law, when a non-volatile solute is added to a solvent, so like say a salt is added to a solvent, okay, the vapor pressure of the solvent decreases in proportion to the concentration of how much you added. So why would it decrease? So the vapor pressure above it, let's say, was 5 atmospheres. Well, that's ridiculous. Let's say it was 0.18 atmospheres vapor pressure above it, and you changed it to be 0.5 atmospheres. You lowered it. You lowered the vapor pressure that was required. Okay? Well, why? Well, because if you look at the pure solvent, so this is just an example, right? So here is these are molecules that can come off, they can escape. They're free to do so when nothing's hindering them. But if you put something in there, now those molecules are being held down by something, and they can't as readily escape. Okay? So an equilibrium will be established more easily at a lower vapor pressure based on that. Okay? So anytime you add something, you dissolve something into water, you change its vapor pressure. You lower it. It becomes at a lower vapor pressure. Okay, now with freezing point, you get a depression, and with boiling point, you get an elevation. So if I add something to water, water freezes at 0 degrees Celsius. If I add something to the water, it will freeze at a lower temperature than 0 degrees Celsius. If I add something to water, it causes the boiling point to go above 100 degrees Celsius. Okay? So here you have 100 degrees Celsius, and here you have 0 degrees Celsius. Freezing and boiling point of water. Adding a solute causes a depression in the freezing point and an elevation in the boiling point. Okay? So now instead of boiling at 100, it boils at 100.52 degrees Celsius. Or instead of freezing at 0, it freezes at negative 1.25 degrees Celsius. Okay? So it will depress or it will elevate. And we can actually calculate the change that's going to occur. We can find that. And we can determine what the new boiling point or the new freezing point should be. Okay? So to do that, we use these equations. They're very simple equations. The change in the freezing temperature is equal to the freezing constant of water times it's the molality of the solute. Now, we haven't really talked about molality, but molality is simply, so molarity equals moles over liters. Molality equals moles over kilograms of solvent. But don't worry about this. Anytime you see that, just consider it to be that. Because in water solutions, these are essentially the same, close enough. So for what you're doing, don't worry that that's a little m. You can consider it to just be molality. If we were using a solvent other than water, it would make a big difference, okay? That between molarity and molality. But because they're water, you guys are just going to do, all I'll ever give you are water solutions to do this with. You don't have to worry about whether it's molality or molarity. You can just consider it to be molarity, okay, for all these equations.
What was the
K
K?
is a constant. It is a chart. You look at the chart, you find the constant for the solvent you're using. For cyclohexane, it's 20.5 degrees Celsius per molal. For water, it's 0.52 degrees Celsius per molal. Okay, so there's a chart that you would look that up in. You would find the Kf for the solvent that you're looking to decide how much the temperature is going to change by, and that's the one that you use as your constant. Okay. Boiling point, same thing. Okay. Boiling point, delta TB, the change in the boiling temperature equals the KB, you just need to know what that is, times the molality. Okay? Times the molality. Let's see if I can. Let me make sure I get those constants correct. Okay, so the Kf of water is equal to 1.86 degrees Celsius per molal. So every molality or every molarity change, so if it goes from 1 molar to 2 molar, 1 molar, or so 0 molar to 1 molar, will cause it to change by 1.86 degrees Celsius. If you go to 2 molar, it will double that, right? That's all this is saying. Every degree it'll change 1.86 degrees Celsius every molar change, okay? Every 1 molar change. That's what this means, okay? And the KB, I believe is 0.52, yep. Okay, so the KB equals 0.52 degrees Celsius every molarity change. So from 100 to 100.52, if it's 1 molar. If it's 2 molar, it goes to 101.04. I'm sorry, 101.04. Okay? So that's how much it's going to change. Every 1 molar, it's going to change by 0.52 degrees Celsius. It's going to increase the boiling point by that much. So this is the Kf for water. So for every solvent, there's a different Kf and Kb. And if you were doing it for something else, which you won't be, you would need to know what that constant is. Okay? Okay. So let's look at so how do we calculate these? Okay. So if I want to find the change in the boiling temperature, let's say that you had a 3.56 molar solution of sodium chloride versus a 3.56 molar solution of glucose. Okay? What will be the temperature change for each of these? So for the sodium chloride, what you need to realize is that when sodium chloride dissolves in water, does it stay one single thing? No, it breaks up into how many things? 2. A sodium and a chlorine, right? So that means that every time I put salt into water and it breaks apart, it's going to cause a doubling of the molarity of the particles that are in solution. Okay? Whereas glucose, it's covalent, it won't do that. It stays together as one single thing. So it's not going to break apart. So it's going to be 3.56 and stay 3.56. Okay? But for this one, I'm going to have to multiply it by 2 to find the new molarity of the particles. To find the molarity of the particles, I have to multiply this by 2. What if it was a 3.56 molar solution of calcium phosphate? What's the molarity of the particles? Well, I have 3 calciums, and how many phosphates? 2. How many total particles is that? Ca2 plus, Ca2 plus, Ca2 plus, PO4 3 minus, and PO4 3 minus. How many particles? 5. 5 particles that this is going to break up into when I dissolve it in solution, right? So I need to multiply this by 5 to find how much it's going to change by based on the molarity. Okay? So let's look at the change here of the boiling temperature based on these 3 situations. Okay? So for this first one, delta TB equals my KB, which was 0.52, 0.52 degrees Celsius per molal. I'm just going to say molarity because we're going to use molarity. Times 3.56 times 2, what is that? What is it?
3.7.
Well, it has to be at least 7 point something. 7.12? 7.12. Okay, that's it. Molality. So 3.56 times 2, 7.12 molar. Okay? My molar concentrations cancel, and I'm left with degrees Celsius. So the change in the boiling temperature is 0.52 times 7.12. What is it? What's the change in the boiling temperature here? What is it? 3.7? Okay, 3.7 degrees Celsius. So, what's the new boiling temperature? It starts at 100. What's the new boiling temperature if it changes by 3.7? Okay. Wrong way. Go up. It's an elevation, 103.7. So the boiling temperature is going to increase to 103.7 if I have a 3.56 molar solution of sodium chloride. Okay. What's it going to be if I have a 3.56 molar solution of glucose? Okay. Delta TB equals 0.52 degrees Celsius times 3.56 because I don't have to change the molarity here because it's just a single thing. It doesn't break apart into pieces. Okay? So what is that? $1.85? So what is the new boiling temperature? 101.85 degrees Celsius will be the new boiling temperature of this solution if it's a 3.56 molar solution of glucose. Yes?
Where did you get the 0.52?
Where did I get 0.52? It's a constant. It's the KB of water.
Oh,
Okay? It never changes. It's always that. So you get it from a list or they tell it to you in the question. The KB is this for water. Okay?
so what was the new temperature? Was it, so do we add, we get the 100 and then add what we got?
That's right.
Okay.
So 101.85.
Thank you.
Okay, how about for the last one? So here, my delta TB is equal to 0.52 degrees Celsius times what? 5 times 3.56? What is that? Well, 17 what? 0.8? Okay, so what is my new boiling temperature here? Nine point what? 25? Okay. So what's the new boiling temperature? 109.25 degrees Celsius. So you can see that depending on what thing I dissolve at the same concentration is going to change my boiling temperature quite differently. Okay? So this one's going to change it by 3.7 degrees Celsius. This one only by 1.85. And this one by 9.25 degrees Celsius. Okay? But they're all the same molarity to start out with. Okay? So let's look at it for the delta TF. Okay? 3.56 molar sodium chloride, 3.56 molar glucose, and 3.56 molar Ca3PO4. Okay? So here is your KF. Tell me what the new freezing temperatures are for each of these. glucose. Okay, to find the freezing temperature change for sodium chloride, I'm going to take my Kf, 1.86, and I'm going to multiply it by what? Say it again.
7.02.
Okay. For glucose, I'm going to multiply it by what?
3.57.
Good. And for calcium phosphate, I'm going to multiply it by what?
17.8.
Excellent. Okay. So what is the change in the freezing temperature for the sodium chloride solution?
13.25.
How about for the glucose?
6.62.
And what about the calcium phosphate? Say it again louder. Okay, so these are the temperature changes. So what is the new freezing temperature for the sodium chloride solution?
6.76.
Okay, so where does the freezing temperature start?
Oh, it's 0, just kidding.
So what's the new freezing temperature?
Negative.
-13.24 degrees Celsius. Okay, so basically for freezing, I just have to put a negative in front of all these. Okay, so when the road freezes, what do? They salt it. Why do they do that? Because by throwing salt on it, you cause a drastic increase in the concentration of the salt to water, and it causes the freezing temperature to drop, and it will no longer be frozen. Okay? Based on this freezing temperature change. Okay? So which one is the most effective salt to use to thaw the ice?
Calcium phosphate.
Is glucose as effective as sodium chloride? Should I throw sugar on this road or should I throw the salt on the road? Salt. Okay? And this one would be better. Calcium phosphate would be better than the sodium chloride. Okay? So if you throw a calcium phosphate salt, that's going to be better than a sodium chloride salt because there's more particles, therefore it's going to cause a greater, more drastic decrease in the freezing temperature. Okay, and now we get to molality. We're not going to really focus on this. Moles over the kilograms of solvent. But the reason they use molality in Collegiate of Property is because with the kilograms, it keeps this more constant. Because if you volume, which is molarity is moles per liters in a volume, as you change the temperature, the volume can actually fluctuate. But mass doesn't fluctuate. as you change the temperature. So that's why they use the kilograms here, because it keeps it a more constant unit. Okay, but don't worry about it. Okay, diffusion. So diffusion is the process of having a membrane between two solutions of salt solutions. One is more salty than the other one, and so then there will be a transfer between the two of water, not of the salt particles. The salt particles will not transfer, but the water will, because that's the way it works. Okay, water moves, the salt stays. The membrane is only semi-permeable, and water is one of the things that can permeate through it. Okay, so there will be a transfer of the water through the membrane, and there will be an equilibrium established. So for example, here you have something that's really salty. Here's a pure water solution. Okay, you can see what happens. The water gets pushed this way until there's an equilibrium of basically of the pressures between those. Okay, we call that osmosis, right? The transfer of the water between the two sides of the membrane. And that's why I don't understand the whole learn through osmosis. You're not transferring water into your brain from your book, right? Put the book on your head. I don't understand that whole thing. But anyways, it doesn't make sense to me, but it makes sense to some people. So this you're going to have water transfer through the semi-permeable membrane until they equilibrate, okay? Until they can find. So at first, there's only water transferring one way. But once there's an equilibrium established, the water will start to go back and forth between the membrane. Okay? So osmotic pressure is what finally establishes that equilibrium. Causes it to stop moving, the water to stop moving. Okay? And so once the pressure on one side is the same as the pressure on the other side, they will remain constant. Okay? The transfer of water going one way and the transfer of water going the other way will be the same. Okay? So that osmotic pressure will be established based on this equation. Pi, which is osmotic pressure, is equal to little I, which is the osmolarity, times the molarity, times R times T. Okay? And in fact, those equations that we saw earlier with delta TF and delta TB, on your reference material, you'll have those with little I in it, meaning the number of particles. So for sodium chloride, little I is 2. For calcium phosphate, little I is 5. Okay? So those equations would be delta TB equals little I KB M. Okay? And so you just have to include little I, how many particles there are, and it'll work. Okay? So that's how the equation works. So here for the osmolarity, we have it as well. Now this equation should be very familiar because you've seen it before, just in a different format. PV equals okay? So if I solve for the pressure from the ideal gas law, pressure equals nRT over V. What's N over V? What does that equal? Molarity. So P equals mRT. Okay? So the osmotic pressure is equal to mRT, which we find here. Okay? And we will use R, the ideal gas constant, in this equation, and your temperature must be in what? Kelvin units, because it's the ideal gas constant. It has Kelvin units in its constant. Okay, so calculate the osmolarity of 5.0 times 10 to the negative 3 molar sodium phosphate. So all that this is asking, so it's 5.0 times 10 to the negative 3 molar it sodium phosphate? Yeah. Sodium phosphate. Okay? So basically what they're saying is, how many particles are there here? Four particles. Okay? You have a phosphate, and you have 3 sodiums. So that's 4 particles. So how am I going to find the osmolarity? The osmolarity is simply the number of particles multiplied by the molarity. And I'll never ask you what is the osmolarity. You'll just have to figure that out to use it in your equation to find the osmotic pressure. Okay, I'll ask what is the osmotic pressure, and then you have to figure out how many particles multiply it by your molarity, etc. Okay, that's it. So this would simply be times 4 to find the osmolarity. Okay, so you have 3 sodiums, 1 phosphate. So this times 4, and you get 2.0 times 10 negative 2 moles particles per liter. Okay? Now, osmotic pressure. Calculate the osmotic pressure of 5.0 times 10 negative 2 molar solution of sodium chloride. 5.0 times 10 to the negative 2 molar sodium chloride. What is the osmotic pressure equals what? That's what we want to find. The osmotic pressure. It's at 25 degrees Celsius temperature. Okay. Okay. So pi equals mRT. M takes care of my moles and my volume, R and T. So all I need is the temperature here. So osmotic pressure equals what? What am I going to put in for M? Do I put this there? Times 2. 2 times 5.0 times 10 to the negative 2 times 0.0821 liter atmospheres over Kelvin moles. This is molar, so it's moles per liters, times my temperature, which is what? 298 Kelvin. Kelvin temperatures cancel, moles cancel, liters cancel. I'm left with pressure, the osmotic pressure here. So what is the osmotic pressure of this sodium chloride solution? .45 atmospheres. Is that what you guys found? Okay. So that's the osmotic pressure. Right? 2.45 atmospheres. Okay. So this osmotic pressure can be applied to our cells. And what happens to a living cell when you put it into a solution, a salty solution, or into just something like pure water? Okay? So our living cells have aqueous solutions of salts in them. And that's establishing an osmotic pressure. And that's at equilibrium. Okay? If it's in your blood, okay, and it creates an equilibrium between your blood and the cell. And it will those are isotonic, essentially. meaning that they're the same salt situations inside and outside, okay, that they establish between this membrane, which is a semi-permeable membrane, our cell membrane. So you can have isotonic solutions, which means the same salt inside and outside. You can have hypertonic solutions. Hypertonic means that there's a lot of salt in the solution. It's hyper salty. Okay? Hypotonic means that it's a low salt solution. It's a lower salt solution than the cell. Okay? So what happens? So what happens when you put a cell that has an established salt concentration in it into a hypotonic solution where there's no salt, let's say, so it's just pure water? Is that cell going to increase in size, or is it going to shrivel and crenate? If it's low salt solution, what's going to happen to the cell? Which way will the water move? Is it going to move into or out of the cell? Into. It's going to move into the cell. Okay? The water is going to go inside of it. Why? Because it's trying to dilute the cell so that the concentration of the water inside and outside are the same. Okay? So water is the thing that moves. Salt does not move. Okay? So the salt's going to stay there. The water's going to move in. And if it's a plant cell, that's fine. It doesn't mind that, because you move the water in, it just swells up, and its thick cell walls, they're happy with that. They say, okay, that's fine. And it's just nice, plump, and juicy, right? But if it's an animal cell like our cells, then the water moves in, and there isn't a cell wall, a strong cell wall, and the cell just bursts open. Okay? So this is one of the ways that we would actually collect DNA or something from a cell. You put them in a pure water solution and it busts them open. You can collect their proteins and their DNA and have fun with it, you know? Okay? So that's called homeolysis, water lysis of the cell. Okay? Now, if you stick that same cell, here it is. It has some salt in it, but the solution outside of it is super duper 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 salty. Way more salty than the cell. Now, which way is the water going to move? The water is now going to move out of the cell, right? It's going to move out, and what's going to happen to the cell? It's going to shrivel. It's going to crenate, okay? So it's going to get all dried up. So let's think about this in context of, let's say you're sitting in your bathtub.
Fingers.
You've sat on your bathtub for a long time. What happens to your fingers? They get all pruny.
Mm-hmm.
Why? Water moving in or out? Moving in. Those cells are swelling because hopefully the salt concentrations of your bathtub are lower than the salt concentrations of your cells, and so water moves into your fingers and they swell up, right? Does the same thing happen if you're in your swimming pool? Do you get as pruny? Really? I hope. You can spend hours in the swimming pool, and hopefully your cells don't get all pruny. If the concentrations of the salts and the chlorine and everything in your pool are balanced to the cell concentrations of your cells, okay, in your fingers. Okay? If they're not, then you might want to check that. Okay. Algae starts growing, and, okay. But so it shouldn't be the same effect, because the concentrations of the salts in your pool from the chlorine and stuff that are used are much higher than they should be in your bathtub. Okay, so you won't get as pruny. That's a dumb word, but that's the only way to describe it. Okay, Has anybody ever had water go up their nose? Yeah. Okay. A few of you, definitely. Okay. What kind of an experience is that?
A non-repeater.
Why? Why is it burning? It's just water. It's like the least harmful chemical there is, right? So it's water going up your nose. Well, you have very sensitive cells in your nose. And what's happening to those cells as they get in contact with pure water? They swell and they rupture, burst, right? Ouch. Okay, that's not fun, right? Has anybody ever used like one of those nose bidets, clean out your nose, and you use a salt solution in it? Neti pot, yeah. Have you ever, anybody? You guys are not adventurous, are you? Nobody's cleaned out your nasal. Okay, use a syringe.
It doesn't work.
Okay. But you want to use a salt solution because if you're going to put water up your nose, you want it to be salty because you want to have an isotonic salt solution up there so it doesn't irritate your nose or it doesn't dry it out either. Okay? So you have to have the salt concentrations balanced. Okay, if you're going to do that.
How come the fingers get pruny, like if it's getting too much water? Wouldn't that?
Because they're swelling. So you're
wrinkle.
well, okay. So what do you think what would happen to your fingers if they were shriveling? Would they get pruny? They would get your skin would get all leathery and tight, right? Because it's shriveling up. So if you were sitting in the ocean, your skin isn't going to swell, right? Poor people in the ocean that get cracked lips and their skin starts to crack because it's just like crunching around them. Okay, that's not fun, right? You can't drink the ocean water because it's so salty. It'll just make you more thirsty, right? That's horrible, right? So don't get stranded at sea.
Don't drink the water.
Don't drink the water. No, you're gonna die faster drinking the water. You're just gonna dehydrate even quicker. Okay. Okay. All right, aqueous solutions. Water. So aqueous solutions are water solutions. Water is the most abundant liquid on Earth. 60% of our body is water, and our blood because it transports all of the ions, it dissolves everything in it and gets it to where it needs to go. Okay, including all the gases like the carbon dioxide. Oh, here's a fun little thing. This is vinegar, very salty. You put the pickle in the vinegar, and it shrivels, right? It crenates, and it goes into a cucumber. Oh, I said that wrong. You start out with a cucumber, and it goes into a pickle. What am I thinking? Okay. So you start out with a cucumber, and it's a very salty solution, so all the water is doing what? It's moving out of the cucumber and making a pickle. Okay? So that's a fun thing you can do at home. Oh, another one you can do at home. This is fun. You can take an egg, put it in some vinegar. It dissolves dissolves the calcium shell. The vinegar dissolves it away. Okay? And then you're left with this thin membrane around the egg. Okay? I would hard boil it first. Hard boil it. Well, maybe you don't know. Yeah, hard boil it. You don't want a big mess. So hard boil it, and then what you can do is take that egg that is just a thin membrane now, because you got rid of the shell. You put it in a really salty solution, and the thing's gonna swell up. It'll even be bouncy. And then you go stick it in a pure water solution. Oh, I'm sorry, I said that all backwards. You put it in the pure water, it swells up. You put it in a really salty solution, and it's going to shrivel up. Yeah, it's fun. Okay, fun with chemistry. All right, don't worry about that. Okay, so these are some important ions that are in your body. Sodium, potassium, you got to have these things. That sodium and potassium are actually very important because they are found in your nerve cells. There's this fun little pump called the Sodium-Potassium Pump in your nerve cells. And it creates a differential charge between the inside and outside of the cell. So you have 3 potassiums, 2 sodiums, and then you open these gates that allow for them to equilibrate. And when they do that, it causes a nerve impulse down those nerve cells because it's an electrical impulse. It's like conducting electricity down your nerve cell. And as it does that, it's sending a message. So when I do that to my finger, I feel it because it's sending the message from my finger to my brain. My finger doesn't actually feel anything. My brain is telling my finger that it feels something. So if my nerve wasn't working there, I would feel nothing. Like when they put anesthetic, right? They put an anesthetic there, it blocks that nerve impulse, and they can stab you with stuff, right? The dentist stabs you, they drill into your tooth. You don't care, you're like, hey, no problem, whatever. That's not any big deal, I can't feel a thing, until it wears off and you're like, ah, right? So, so it's your brain that's telling you that you're feeling something. And those nerve impulses, you got to have sodium, potassium. You have to have calcium to move your muscles. So all these ions are so important in our bodies. You got to have them. Okay, so active transport, yeah, we don't need to necessarily focus on all this, but fun. Our bodies are amazing. That's the bottom line here, right? That if you think about every little thing, every little tiny cell in your body and all the processes that occur in every single one of them, all the time, day after day after day, if something stops working, it's going to mess you up, right? So, but they work. It works. And it's just like millions of these processes that are just taking place all the time. It's amazing. And they work. Okay? All right, guys, we'll see you next time.